Hi, I'm Marco from AI2S, and welcome to the third and final lecture of our Julia course. In this lecture, we'll see how to use some specific Julia libraries to solve differential equations, to create probabilistic programming models, to use distributed programming, and to benchmark different code implementations. Note that also, the notebooks for these lectures are provided in a GitHub repo. You'll find the link in the description. Unfortunately, due to technical problems, the very first moments of the lecture were not recorded, but it shouldn't be an issue as only the introduction to the first library was lost. Now, I will leave you to the recordings. Have a good time.
The idea is that with this package, we can have model many different kinds of differential equations and solve them numerically without, say, too much difficulty. Let's say we will start with a very simple ordinary differential equation, the usual, that du over dt is alpha times u. That is, which is probably the first differential equation, one of the first differential equations that you can see in any course. Which simply means that the instantaneous change is given by multiplying by this parameter alpha. So we say alpha, and how can we define this differential equation? With Julia, we have this structure, which is a function that is always receive three parameters, which are the current state, set of additional parameters that we will see how we can find them in a short time, and then t, which is the current time, since we are imagining differential equation and modeling how something changes with time in a continuous way. So we say alpha is 1.2, and we simply, what is the instantaneous change is 1.02 times u. In addition to this function, we also need two additional informations to solve numerically the differential equation, which are the initial state, the initial condition. In this case, we call them u0, which is we start with 0.03, and the time span as a pair. We start at time 0 and we want to end at time 1. Now we have all the ingredients to define our problem for ordinary differential equation. We see ODE problem, which is the function f, differential equation given by the function f, initial state u0, and we want to solve it for the time span given here between 0 and 1.0. And this returns a structure of type ODE problem, and we will investigate a little bit in future what are some of the additional information that we have saved in this structure. To solve the equation, we simply call the solve function. Usually, we only need to provide the solve function with the problem to solve. Notice that it is not usually necessary to specify explicitly a solver, but you can if you check the documentation. Let's go to the documentation. We'll share the other Pi. We have ODE solver, and we have a collection depending on the stiffness, if you have stiff or non-stiff problems. The usual solver that you find in for MATLAB, Python, and R, and then a very complete list of, as you can see, it's quite long, all possible methods that you can select. In addition to selecting explicitly which solver to use, we may also give some kind of hint. Let's say this is a stiff equation. This is given by the keyword algorithm hints, and with the symbol stiff, for example. As always in documentation, you can find all the hints that you can give to the solve function to help the function decide which solver to use. We can also decide if what are the relative and absolute tolerances in solving the equation. We can simply solve now problem with the default solver. We're able to solve it, and what we have is an structure which represent our solution, and we see that we have performed 5 evaluation of the function in those for those values of t, and we're obtaining those values of u. We can now plot. We can see the solution and what is the analytic solution defined with dashes. Notice that, in fact, what we have is not simply this 5 point, but what we actually have is something more. Well, as you can see, well, this is one of the simplest kind of differential equation. This works well, the solution. But what we have here is that the structure given by the solution can also be used as a function. In fact, for example, here we obtain the value of the solution at 11 different points. And this is because it also provides an interpolation of all the points where the function has been evaluated. You can also control which kind of interpolation to use, but the default is quite reasonable. And as I said before, you have this as fields. And the structure, we have t, the value of the time, and u, the value of the that the function assume, that have been, where the function has been evaluated, that we can access directly. So in some sense, we have everything we may need for a solution. Actually, there are also a lot of other things that we can extract for the solution, but say the basics are all here. And one thing that you may have noticed is that the function f before did not have had a parameter that we have not used. Well, we know that t is the time. We know that u is the state, and then p. What is p? P's are the parameters of the differential equations. So instead of using an high-code parameter alpha, we can say the parameter can be any structure, or can be an array, can be a tuple, can be a simple number, as in this case. We say that p is our parameter, so this is actually not a single equation, but a family of equations depending on the value of this parameter p. And the interesting thing is that now, when we define the ODE problem, in addition to the function, the initial state, and the time span, we can also pass as an additional argument the parameters to pass to this function. as you can see, we now have a new ODE problem that we will get the actually the same solution. This is an example how we can change some of the call to the solve function. Instead of calling simply solve, we decided which solver to use, which is the relative tolerance and the absolute tolerance that we can accept. As you can see, we have still the correct solution. Except that now, if instead of using alpha, that was 1.01, we want 1.03, 1.03, yeah. We don't have to redefine everything, since it is simply an additional parameters that we pass to ODE problem. So we can define an entire family of differential equations that have one or more parameters, and simply pass the parameter when we create the ODE problem, and we pass them the problem to solve. And one little thing that you may have noticed is that, well, it's an ODE problem where the state is a float 64, the time is float 64. We know the time span, the initial state, in place false. This in place false is quite important from the performance point of view. Why? Because in place false means that every time we evaluate a function, for example, g, that we are going to see, or even f, for your f, what we are doing is that we are creating something that is returned by the function. Here is simply a number, but since we can return entire vectors, simply means that every time we evaluate the function, we allocate a new vector, the vector is then returned. An in-place evaluation means that we have an additional argument that we modify, and in where we save the new value, the output value actually. So for in place, for example, we want this in place evaluation. In this case, we use, since we will use also in the next examples, a vector of size 1 in this case. So we have f, we use the bang at the end to mean that we are modifying one of the arguments, in this case du. The first argument is, we have 4 instead of 3 arguments, is the arguments that we are going to modify. It will have the same shape and size of u. So du in position 1, the next value is p times the value of u. And when we call ODE problem, now since it has 4 arguments instead of 3, we know that we have in place. Everything will be evaluated in place, meaning that every time we evaluate the function f, instead of having f allocate something, turning some new allocation, it will simply modify one of its arguments. But apart from that, everything else works exactly as before.
Excuse me, what was the difference that turned the in place into true?
The difference is that we have 4 arguments instead of 3, and we modify the first argument. Instead of returning the solution, returning a value, we modify the first argument so that what we should have returned with only 3 arguments is instead saved into the first argument.
Okay, thank you.
Okay. So to see a little bit more complex example, we will try to model the predatory Pi system with the local voltage equations. In this, if you don't already know them, the local voltage equations represent the behavior, try to model the behavior of a predator and a prey population, and we have the x representing in this case the amount of preys, and y the predators. We assume that the prey grows with the rate alpha, which is how much they increase in number. We assume that in the environment they don't have any scarcity of food, and the number is reduced by beta by x times y, which means that as there are more prey and more predators, the number of preys is reduced more, because because actually there is more encounters between predator and prey. Similarly, not so similar, the number of predators increases with the number of predators and prey, and it is reduced by a certain value that is proportional to the number of predators, which means that the predators died or left the territory. How can we define them? The local voltage equations in place? Well, we know that we must have 4 arguments: u, p, and t. So for simplicity, we say that in P we save everything as a tuple, and here we unpack the tuple so that the parameters are alpha, beta, gamma, and delta. So we'll have the first element of the tuple in alpha, the second in beta, the third in gamma, and the fourth in delta. X is the first element of U, Y is the second element of U. And as you can see, now that we can define what is the change, this tangent change, is simply a rewriting of the equation that we already have. So if we want now to solve this ODE problem, with a system of equations, we have that we have to fix an initial state. Instead, we said that the number of quadrant points is 10, the amount, and we have these parameters. Notice that we can use a simple tuple, or we can use a named tuple to improve readability, so that we remember what parameter is what. And then we set a time span, for example, from 0 to 100. And as before, we can simply call solve. And to solve this system of equations with this initial condition and those the parameter that we have set, and we can plot them. And as we can see, we observe the usual behavior of the number of preys increased. So with a certain delay, this number of predators is increased. Then since the number of predators has increased, the number of preys, in this case, is reduced, and as a consequence, also the number of predators, since they don't have any more preys to catch, and so on. So this is for ordinary differential equations. This is say those are the basics. So if there is any question, also in the chat.
excuse me, do we need the, I mean, when we have two dimensions, we need to identify the x and y element of the u vector. But when we have only one dimension, it is necessary to specify the square brackets with like, for example, the first ordinary differential equation you made.
Okay, no, it is not necessary because you can simply pass, instead of a vector, you can pass simply a number. But if you have more than one dimension, you want to pass a vector.
And so we need to identify with the square brackets in the second case. We need to identify the positions. Oh.
Well, actually, we don't. I used x equal u1 and y equal u2 only for readability, but we could have used u first element, the second element in this way, right? Simply for readability. So this is actually the same, except it's a little bit less readable, since we have to remember that what is in, since we use notation with x and y in defining out in writing the local equations, we have to remember that x is the first component, y is the second. Except from that, there is.
Okay, the OD problem function recognizes the. Okay, thank you.
Okay. Is there any other question? Okay. So let's continue to observe that there are, in fact, many other kinds of differential equations that can be solved and using differential equation the differential equation GL package. And it is simply taken for the documentation the list of kind of equation, and actually, to be honest, some of them I've actually never used. As you can see, it is quite complete. And one thing that we will model now is the SII model using discrete stochastic simulation. In this case, with using the Gillespie model. So the Gillespie, the SI model, we probably have heard of it a lot of times in the last few months. Is a model to simulate the diffusion of a disease inside the population, where each individual can be anti-susceptible, so it can be potentially infected with the disease, can be infected, and then when it is infected, it can transmit the disease to other susceptible people. And finally, they are recovered, which is the people that have cannot catch the disease anymore because they have achieved immunity or they have died. And we know that we have two parameters in this model. We know that a certain rate on which the people moved from susceptible to infected when a susceptible person is in contact with an infected one, and a rate at which the infected go to the recovered state. And one thing that we can use that works and it is built exactly because it works well with differential equation.jr, is the Catalyst package, which allow us to build what I call reaction networks, where we can write more or less what can be thought of, for example, as chemical reactions. If you use some chemical reaction networks model, and you have we have this macro at reaction networks, and then we write all the reactions. What are reactions? Well, we say that we iterate C1 are susceptible and uninfected. I transform them into two infected, which means that the susceptible person becomes infected. And we iterate C2 uninfected, go to the state of recovered. After the end of this block of reactions, we say that what are our parameters, C1 and C2. As you can see, this is a case in which the macro, the ability of writing code using macros in Julia helps us because we are actually using what's called our domain-specific language, which is this one that is not normally valid Julia code, except that inside this macro, it is then rewritten into valid Julia code, but it is a lot more readable for us. Yeah, we are actually writing a reaction with all the reaction and the rate. So now suppose that you want to check this in this time span, time span between 0 and 300. What are the parameters? Is a tuple. In this case, will be C1 and C2. C1 is 10 to the minus 4, so, and C2, that is the probability to go from the rate at which infected becomes recovered, is 0.01. We start with the population. The population will contain all the three species, S, I, and R, in the order in which they appear into the reactions. So first S, then I, then R. And of 1,000 people with 999 susceptible, 1 infected, and 0 recovered. And we said that this is not an ODE problem because we want to move in discrete steps. We say that it is a discrete problem. And then we can solve it, and without going into the detail, because we can simply say that this problem can be solved with jumps of uniform length. We consider jumps of uniform length. We use this kind of step and so on, since there is a large family of kind of problems that can be solved with in the library differential equation.jr. I'm not going to explain all the different solver and so on. Just know that for more or less any problem that you can define, you usually have some, if not many, some, if not maybe more, all the common solvers. So now we perform this simulation, and we can plot the result. And as you can see, this is similar to a lot of the plots that we have seen in the last few months when we have the susceptible. Well, usually we don't see the susceptible, we know the amount of infected, then we reach a point where most of the people are either infected, and we end up with having a difficulty finding new people to infect, so the number of infected go down while the number of recovered goes up. As an exercise, you can easily expand this reaction network to contain additional and more complex model. For example, we can have a model that distinguishes between a recovered and a dead person. We can write a model that distinguishes between a moment when the patient is infected, but has no symptoms from the moment when the patient has symptoms. So the rate of infection go down because usually it is isolated, or should be. And this is all quite easy to perform since we can write everything as this reaction network. Or we can use, as before, the ODE problem, and instead of solving this discrete version, in which we actually count the number of individuals, the continuous version when we have say standard ordinary differential equation. And this ends this very, very short introduction to the package differential equation of JR. As you have seen, for the number of different kinds of differential equation that I supported, that this is actually a very large and interesting package. I suggest also to check two other packages. If you are interested in mixing differential equation and neural networks, okay. If you have some, if you want to mix differential equation and neural network, you can use Discrete Flux that integrates these two packages, and you can define, for example, neural ODE, which are a very interesting kind of mix between a new differential equation and a neural network. If you know, residual networks can be interpreted as a very raw approximation of the solution of a differential equation using the normal Euler method. And you say, why should we use the Euler method? It is not the best one by far for solving this differential equation. And you use another kind of solver, so you obtain something like a neural network where the number of layers, the depth of the layers, you can think in some sense, is not fixed. And maybe you have a lot of code in Python or R, and you can actually use all the solvers and everything from differential equations by using the two packages diffq-pi or diffq-r that are available on PyPy and on CRAN. You obviously have to also have Julia installed with differential equation installed. And I see a question: is there some special meaning of saying C1, C2 after an interaction network? Yes, there is a special meanings. It means that the parameters of the actual network are C1 and C2 in that order. Okay, is there any question regarding this part? Oh, I see now that I have a typo.
Excuse me, are you saying that in Python and in R we can import the packages diffq-pi and diffq-r respectively to use the solvers of Julia?
Yeah, to use more or less everything from differential equation of JR, as long as you have Julia installed with the module differential equation.jl installed. Obviously, because you need to use it. But then you can call the same function from R or from Python.
And maybe just the solvers, the rest of the methods to write. For example, I remember that I used the SymPy to define systems, network systems, like the one you use for Lotte Volterra and
Okay.
in Python, and then we can use the solver as different.
Yeah, actually, you can use most, if not everything, from the package. In particular, you have access to the solvers. You have some things to check, for example, because in the name of some function are for example, in the Python version, which is the one I know a little bit more, is has some differences. For example, if you have something with bang at the end, this is not allowed as a valid function name in Python. So you have underscore b at the end in this case. So some function names are a little bit different, but nothing too difficult.
Okay, thank you.
Okay. Is there any other question? Okay, so let's go forward with the probabilistic programming. First of all, before going into the specific package, I want to spend a certain amount of time talking about probabilistic programming and why it is important, why you may be interested in probabilistic programming. Well, first of all, if you think about normal programming, what you have is you have a set of initial parameters, you have a certain model that you can think as an algorithm. You run the algorithm on the parameters and you obtain a set of results that you can think of data. So you have the parameters, you have the model, you want to generate the data. Now, with probabilistic programming, you actually have a different approach. What you have, you still have the model, you have the data, but you have no knowledge about the parameters. So, for example, you may know, maybe the data, let's say, from this plot, which means we know how the number of infected, of covered and susceptible people has changed with time. We know that SII model, we don't know the parameters C1 and C2. And we want to say, okay, what are the parameters that are the most plausible one for generating the dynamics that we have observed? You may think, well, this is statistics, actually. Yes, I agree in this case. This is statistics, except that we are writing it as a computer program. So in some sense, this mix in which you define as a program a model, and you say, okay, now I give you a solver, some kind of solver, let's find the parameters that we need, that were the most plausible for the data that we have. We will see some example to say, okay, we have a coin, we are flipping a coin, we don't know if the coin is fair or is not, and we want to find the probability given a set of flipping of this coin, if the probability for the coin to give head or tail. And to do this is still a domain-specific language introduced by the model function, the model macro. And this is all defined in Turing. Then I imported two additional packages. One is distribution that allows us to define multiple probability distributions, and micro-chain Monte Carlo chains, which simply is used to get a set of solvers or samplers. So suppose that you have a vector of samples, y1 and yn, let's say, or 0 and 1, depending on the coin was head or tail. We know that there is an unknown parameter for us, p, that is used when flipping the coin. The coin are flipped with a Bernoulli distribution with parameter p. All the same, because the coin is one coin, is always the same coin. So model is simply, in this case, a function that will take as input one of multiple inputs that are all our data. We say that p, we actually don't know what is p. We have to define a prior. In this case, we use the beta 1-1 distribution, which simply means we know nothing about how the probability of landing on head for our coin is. Then we say that for each element in the vector that we have obtained, well, the element should be distributed according to a Bernoulli distribution with parameter p.
Excuse me.
Yeah.
Y is the vector of the samples. Yet when we compare, it is usually a random variable that is compared to distributions, right? Because we are saying that the samples of the vector y are sampled from a Bernoulli distribution by writing this, by using the tilde.
What we're saying is that we expect so just imagine this not as something that we already know why. Just say, okay, we extract p from this probability distribution, then we generate a series of extract from a Bernoulli distribution with parameter p a certain number of samples, which can be n samples. Okay, and this is the model that we can use to generate our sequence. Except that now, what we want is, okay, we know that this is the model used. We know what we have extracted. So what is the most likely p, given that we know what was extracted? But hopefully this will, the next example will clarify. And because let's get our data. That is, we generate with a Bernoulli distribution with is a fair coin, 100 flips of a fair coin. Actually, let's see, we have 0, 1, 0, 1, and so on. One interesting thing that you can do with the rand function is the first parameter is a distribution. Then all the numbers will be extracted according to that distribution. So we now know what are our data, and we say, okay, now we want to find what is P. This part could be something that we already have. We don't know how. We want to find again this parameter is 0.5 or be near this parameter 0.5. To do this, we use this sample function. When we pass our model with the data as input, then we say two things: which samples to use. In this case, is Hamiltonian Monte Carlo, and how many iterations to perform? 1,000. And what you will obtain is that everything is then compiled, and we sample. We're performing this sampling. And the end result will be a value of, so we have P, we have a distribution actually on what should be our value of P. We have with mean 0.4895, standard deviation 0.0473. And if you plot the histogram of what could be P, you know that exactly is peaked near 0.5. So we know that probably our parameter P will be somewhere near 0.5. So this was a very informal introduction to what is probabilistic programming and why it can be useful. The idea is that every time you have a model and you have the data, but you don't know the parameters, instead of writing code to actually update our probabilities, to trying to find what were the parameters, it is easier to simply write the model and call this sample with our data and our model, and then find what were or a distribution on our parameters. Well, this is a very simple example. And in fact, I want to point out that the documentation of Turing GIR has a lot more examples that you can follow. Let's go. Yeah. For example, instead of doing this sampling, we can use Bayesian neural networks. So we can build the entire neural network, and you can perform more or less everything from this simple example that we have done to variational inference. And we'll not go into details on all of this, but I think this is a very interesting ways of approaching this kind of problem, and certainly simply that doing everything by hand. There are some other similar frameworks, in this case I know for sure for Python, but I think the syntax is a little bit better, and it is with Julia, and also quite fast in this inference part. Is there any question about this probabilistic programming?
I have a question. In the histogram, we are showing the p's, the distribution of the p's. If I remember correctly, by my stochastical modeling and simulation course, the Hamiltonian Monte Carlo performs a visit of the state space by moving according to the Hamiltonian function. Just in short, we are using the points of the data as starting points for the Hamiltonian tour, for the Hamiltonian visit of the state space, and we are seeing here the final result. Because we started from a data set and we got to obtain another data set, and I'm not very sure about what we got.
So what we had actually, independently from the Hamiltonian Monte Carlo that we used, is that we started with this prior on P.
Which should be a constant, right? Beta 1 is a constant, right?
And then we had the data, so we have the data prior given the data. And this is how we have updated it actually.
The update of the prior, okay, according to the Hamiltonian Monte Carlo.
Yeah, depend on the solver that you use. Now it's Hamiltonian Monte Carlo, but let's see if I can show which different solvers we have. API, no. If I can find again where there is some list of all the samples that you can use. Maybe in samples visualization, you can see Gibbs, Monte Carlo, MCDA, no U-turn, and so on.
Yes, this is all the.
You can. This is something that you decide when you you have your model. Well, and you have to decide which sample to use to find the parameters. So I didn't want to go into too much details, or actually since this say this part would be more on from the stochastic modeling course, why I want only to introduce the fact that there are some tools that can help in automating most of the things that that you can see in the different courses.
Thank you.
Okay. Is there any other question? Okay. So let's move forward. And one interesting thing in Joule is that it already has all the tools that we may need for performing distributed or parallel computation, or also computation on GPUs. And in this case, we are only exploring one case, which is distributed across multiple processes. Remembering that those processes can potentially be on multiple machines. But in addition to this, we also have possibility of using multi-threading, or also the possibility of increasing the serial performances, for example, using the @cmd macro. The @cmd macro, for example, forces to use the vector instructions if they are provided. And then we can also use with cura.gil directly graphic processing unit. And this is usually quite simple because in many cases what we have is that if we are working with arrays, for example, you have a different kind of arrays. Like last lecture we saw that we have, for example, pi vector for the arrays that are for the NumPy arrays. And well, we can use, for example, CUDA vectors or distributed vectors or shared vectors and so on. And everything that works with a generic array will work with those different arrays, except they maybe they live inside different processes, different or inside the GPU or different shared between different threads. So let's start by using distributed, and then we will use also benchmark tools. So how many processes is currently using our version of Julia? 1. Well, we can actually add additional processes with add proc. And we are starting a new process. Well, let's start another one. We are now at 3 processes. Now we have 3 Julia processes in the same machine, and they can communicate between them. And we will see how they can communicate using that at everywhere macro, spawn at, what is a future, and how we can use fetch, what is sync, and what is distributed. Okay, so everywhere is something that say, okay, execute the following block of code into all processes. The macro will provide the code so that it is distributed across all processes and every process run it. Spawn at require an argument, say at which process, a process ID from 1 to the number of processes. And which function to call there. This will immediately return, but it will not return the value exactly for the execution by a future. A future means that we have something where we will be able to call fetch on, and the fetch will return will block if the value was not computed, was here the eternal value of the block of code that we spawned in the other process has not finished to run, and if it has finished, we'll have back the value. Can use sync to wait for all processes to complete their work, and we will see how we can use distributed to simply distribute work and gather then all the work without using explicitly spawn at everywhere and sync. As our test function, we will use this function at approximate pi in a very way by simply sampling n times between a point in the unit square, and then say, okay, is it inside or outside the is inside or outside the circle of radius 1, and 4 times the proportion between the number of points inside the circle of radius 1 and the number of sample point will give our estimate of pi. Actually, let's add box pi. If you want, you can use separator to make everything more readable if you want. 3.141. Yeah. And then let's do this. We can use benchmark tools. We use here btime. And btime is simply a variant of benchmark, another marker similar to benchmark, except that it returns only the final time of the execution. So this is how everything is executed into one process. Notice that we haven't used anywhere the macro everywhere, spawnnet, or any other macro. So we take 62.3 milliseconds. So what can be a strategy to parallelize this? Well, we can spawn and define in any process a function that computes the sum of, not of n elements, of n sample, that those not n samples, but only n divided by the number of processes that we have. And then each computation will return a future. And we will wait for all computation to halt. So maybe if we want to compute on 10 processes with 10 to the 7, so 10 million samples, we will give 1 million of point to sample to each process, and then we will return the sum of all of them. Fetch, and then we compute the approximation. So the approximation of pi simply say that for the first endpoint, well, this is actually the same, except that instead of dividing everything by n and multiplying by 4, we'll do it once at the end. So this is simply returns this sum. Notice that we have prefixed to this function the marker everywhere, meaning that this function is defined into every process. This is important because otherwise when we will try to spawn, that is to call this function in another process, if the function is not defined there, well, obviously the process will return an error. So record that if you want something to be available into every process, use the marker at everywhere. For example, even for libraries, you use at everywhere, and you say using and the name of the library, means that using this import will be done for each process, and you will have the library available on all the processes. So let us compute pi. We say we have np's number of processes. The partial sum from the different results is a vector of size np, initially empty. We divide everything in chunks of size k, which is the integer division between n and np. And then we spawn in each of the process I for 1 to the number of processes, we spawn a prox pi sum with only k samples to do, and we set the result in Python sum. This will be a future. And why we use sync? Well, because we want to exit from for a cycle at the end, only when all the work has been completed, that is, we have filled this partial sum array. And one quick note, potentially if the number of processes that we have is not a divisor of the number n, we may have some missing value. That is n minus, that is the remainder in this case. And we simply do this at the end in the main process. So we sum what? Well, first of all, we fetch all the partial sums, that is all the results of computing approximate by sum. And then we sum all of them plus the missing pieces that we had at the end. We multiplied everything by 4. We divided by n. So in this case, we have something that scales with the number of processes. And we can use compute pi, which I warn you in this case, since I'm on a I'm working on a dual core processor, and at the same time performing this stream, probably will see practically no speed up. But if you use it, for example, on by spawning maybe 10 or 20 processes on a machine that has 10 or 20 cores, then you will see a good speed up. You see that we have a small speed up from 72 to 57 milliseconds. So we have a speed up not good because, as I said, we only have two cores on the machine I'm using. So, but the fact that of splitting the work, question the allocations I need for the at everywhere macro. Well, more than the at everywhere is because, well, we are allocating allocating a vector. So certainly we have this vector when we save the intermediate results. And we also have the few twists that are torn from the spawn that, well, they need to be allocated somewhere. Yeah, we usually have, in any case, we usually have more allocations because we have also more bookkeeping in the mid, because we have to save the few twists and then fetch them. But, well, in this case, you are trading a few allocations for a speed up, and the number of allocation is not that bad, even if you move to a machine with a lot more cores. And the speed up is a lot more significant in this case. And, but in fact, this is something so common, the fact that you say, okay, split this for cycle among multiple machines, and then collect the result using some function. Okay, there's a question when some fetch by session we put plus s, as has been defined, is there some main process. Okay, s is defined here. And this is because, for example, if we have, in this case, 3 processes, and we have 10 million samples, 10 million is not divisible by 3, we will have that if we use here k, the integer division, okay. So this is only to avoid sum also what we could have missed with this integer division, the remainder of the integer division. So as I was saying, this split and collect is so common that we have the @distributed macro, which how it works is distributed, then the function on which to merge all the results, and then usually we have a for each cycle, say, okay, execute this for each cycle, distributed in chunks across all worker processes. At the end, collect the result of each cycle, which is this one, the last instruction of the cycle. Collect the result and sum of the result with plus. So at the end, we will have the sum of all, and then we simply have to multiply before and divided by n. As you can see, tends to work. And as before, there is this, since you're working at two-core machine, I'm not sure you will get any significant or will get any speed up. Yeah, we get some speed up, 44 milliseconds. We started with 72, is not a 2 times speed up. And as you can see, we have some less allocation, because one important thing is that while here we're doing everything by hand, and if we want something particular, we can do everything by hand. The distributed is also quite optimized to avoid moving too much information between the processes. And in fact, with this distributed Pi, actually, now you have something that scales very well with a number of processes. Well, this is not everything, because in fact, I will say this C also, which is more or less essential, very useful, is that if you are used to program everything in using MPI, well, there is a binding for MPI using MPI.jl. But many of the features of MPI, you can find it in the distributed part. In fact, probably the ones of you that are familiar with MPI probably will call that should have seen some similarity with this distributor. Of also, you can have something similar to OpenMP with the thread interface. You can use distributed arrays. Distributed arrays are quite interesting, because what the library provides is actually only a data type, a distributed array. And you can say, okay, take this array and distribute it across this set of processes. Usually, you can also decide the shape in which the distribution happens. You want to distribute it in maybe rectangular chunks, so if you want to distribute it by row, by column, and so on. You can have access to each of the arrays, except that for everything that is not local, you will obviously pay a penalty, because you have to ask to another process, possibly on another machine, to retrieve the data. But you also have some views of the array that are only the local parts. For example, if you want to implement something where most of the interactions are local and you have only on the border some interaction, distributed arrays is quite natural, because you write everything that works with standard arrays, and you can use it with only small changes with the distributed arrays. And then finally is, if you use GPUs, I suggest you to check Julia GPU, and in particular the CUDA.jl package, which is the most well developed, where you can have most of the CUDA exposed in a natural way to Julia, and in particular, we have this QRA type, CURA, that is an array that lives on the, or a matrix that is allocated on the GPU, and where most of the operation works on the GPU. Remember that by multiple dispatch, for example, we can define the plus between two CUDA arrays to be a completely different code from the plus of two standard arrays. So the plus of these two CUDA arrays will be something that works entirely on the GPU. And we have seen Flux last week for defining neural networks. And things notice that Flux is very well integrated with for the use of GPUs. And in fact, you can simply usually use these GPU, open parents, then the model, then close parent, then, and also the same for the data, to allocate everything on GPUs and perform all the training using GPUs. And you may find that, in fact, there are other packages which I'm not actually familiar with, except for their name and why they're used, that allows also to work on tensor cores or on tensor processing unit, and on other kinds of GPUs that are not the NVIDIA ones. So with this, I have completed that. As I said, as you said at the beginning, it was a quite short lecture, because now it's time for your question about this Python distributed, and then for general questions about Julia that I will try to answer at the best of my possibilities. So
I have a question.
Yes.
If it's possible.
Yeah.
I would like to ask about the MPI.
Yeah.
Is it so the interface for MPI is similar, or does it implement more or less all the functionalities of MPI? For example, MPI IO and these sort of things.
I say that the Pi that I've seen, well, the Pi that I know and you have use of MPI were also implementing MPI.jr, and I haven't checked if everything is actually covered or not, but it is, I think, it is quite, at least for what I've seen, it is quite complete.
Okay, so the majority of the things you can do in MPI, you can also do in Julia.
Yeah. Even
okay, thanks.
One thing that maybe I suggest is, since MPI is only binding, you may want also to try to use this distributed library, which is, in my opinion, a little bit less old-fashioned, because one thing that, well, you probably know when working with MPI is that it really feels old-fashioned as a way of computing. Okay. So can I recommend a package for genetic algorithms? There are not that I know of. It is in my list of to-do things to write one, since it is genetic algorithm. And, oh, someone know it, evolution.jr. It is, I don't know how complete it is, because mainly I work on genetic programming, and this time I checked, the things I do were for genetic programming where I wasn't able to find. So thanks, because I was not aware of the state of evolution.jr. Okay, so Is there any other question?
It might be something that you already covered in the previous lectures, but I can't remember at this moment. So can we produce an executable that is possible to run in most machines without having Julia installed in somehow?
I would say yes and no. Let's say it is not. The thing is, everything you will ship will have embedded inside it. Well, you can have ahead of time compilation with something like package compiler for the specific packages, except that every binary you will ship will contain inside actually a Julia compiler, because you can define at runtime and compile say new code, and so you need in some sense a compiler if you wanted to have the complete power, say, of Julia. I know that there is work on ahead of time compilation, for example, this package compiler, and I prefer to see Julia as what's called an image-based language, which is something that things like Common Lisp is, for example, which means that you actually have a kind of image of state of a machine. In fact, if let's see if I can find was save image. No, I was importing with another package. Saving the image file of Julia, which is the things that is loaded when you load Julia can also include, let's say, all the packages that you want loaded at the beginning. Say so, it is strangely, it is not a so easy question, and well, I think many languages that have things like marker and ability to define, run, and compile code at runtime have this problem that they actually need to ship with an entire compiler.
Clear, because I was thinking the problem to use it on clusters or my facilities might not have Julia kind of installed.
Yeah, but in this case, if you are, I have used it on clusters where there was a directory mounted on storage mounted to all the nodes of the cluster, and we're using actually a local installation of Julia, and everything was local. So in that case, everything works. But for other,
Yeah, no, it's clear. I'm completely understand.
it is actually has been used for very large computation. In fact, I suggest to look at this presentation, which is slash.jr, which is one the example of beating the petaflop barrier using only Julia in a distributed manner, which is something that only C, I think, and Python have achieved. no other language has run on more than a petaflop computation on a single program requiring more than a petaflop.
Okay.
Okay. Allora questo I can define a data frame constructor at a times sigma, where times sigma is a newly defined structure by using multiple dispatch. I mean, I would like to delegate one of its constructor on times sigmas. So for example, we want to define for a data frame, or you want, yeah, this is actually quite similar. Let's work it with something that work with that it works with that with data frame, or actually with any struct. You can overload actually the constructor and have multiple constructors. Oh, sorry. So you can have multiple, let's say, create extract foo as x, y, and the array of something, array of maybe not times sigmas, float 64. One dimensional array of float 64 is actually equivalent to calling foo with p and y. And you can actually have multiple, for example. You can have this, you will not call this constructor, but if you have this, as you can see, you call the constructor. You can actually have a constructor with different arities, constructor with different specialized with depending on the type. So for example, you have foo, the time is y, you don't specify which y, or maybe you specify that y is int 64. Now what you want is foo yy. So you can do the same for for every structure that you have in Julia. You can simply define a new constructor with the types that are specialized to what you want, and then you can do more or less everything in between. It can be a simple function. This is, I hope this is clear. You can define multiple constructors. So then you have this new constructor that works only if you have one. First is int, the second is float. And Julia will always take the most specific one. So if you have one that is defined be only for any type X and any type Y, and one that is defined for int64 and float64. When you pass an int64 and a float64, you will get the more specific definition. If there is ambiguity, then you will have an error, because there are some contrived cases when you can force an ambiguity. If you have a constructor and actually you have one that you fix and you specify, you fix the type of the first element of the first argument, but not of the second. Another when you fix the type of the second, but not of the first. There can be some ambiguity in which one is the more specific one. But in general, you can define any constructor. Good. So actually, this is one of the reasons why I like the multiple dispatch approach of Julia, because if there is something that works that I can extend with my types, I can simply define a new constructor, and while everything still works. I can define a new plus function for that sums, instead of numbers, sums, I don't know, dynamical systems together. Well, it works, and then everything that requires only a sum will work. So, is there any other question? I'm here exactly for a question, so feel free to ask. Okay, tool for keep learning Julia or resources? Yes. One thing is the Julia. I will share another. Okay, this is Julia Academy. And there are a few courses. They maybe don't cover everything, but they go more in depth for most of the things we have seen here. Like there is more on Flux, more on parallel computing, more on data frames, in particular the last version of the data frame package. I know them. Well, and this is interesting because computational modeling in Julia with application to COVID-19 is a course where you are actually learning data science and modeling skills for very real application. And another things that I suggest is in julialang.org. You have this learn page, and the YouTube page of Julia has most of the Julia conferences and some of the tutorials. Some of the tutorials are maybe 2 or 3 hours in length, maybe only on one specific package, so they can go a lot more in depth than what I've done here, and they are usually from the creators of the packages. So even if I'm a Julia user, it is different, having the ability to learn directly from the creators of the packages. And on the JuliaCon, the Julia conference, usually you have the many new packages I presented, and in fact, well, you have these long tutorials, and you have some on the last development of Julia, when you can see something that is many of the topics that I presented are maybe new packages or new applications. Maybe also in some cases a lot specific, like, well, let's see if I can find a way. Okay. Something like Stanford Network Dynamics, which means how to model some dynamical system that where all the dynamics happen inside the networks and so on. So my suggestion is, if you, for a more general introduction, you have Julia Academy on all the tutorials, and then if you want the latest development, you have on JuliaCon, you can find talks about the specific packages. Finally, well, the manual for the basics of Julia. Okay. Okay, for the basics of Julia, I suggest look at the manual, because actually this is when I started learning Julia, that was maybe the resource that I used the most, because it's actually quite well written and quite easy to follow. So questo è Miele at the beginning with Julia. I've downloaded the Atom in June, installed that has the editor on the Apple. The question is, what is the pipeline to compile a piece of code and to include the piece of code in some other Julia code and so on, simply using the include name jar? Yes, but I would say one essential package for all of these is Vice.jl. Let's see if I can find where Vice it, because Vice.jl synchronize the code running in the Apple with the code saved in the file. Let's see. Okay, this is Vice.jl. You can install with the usual add Vice.jl, and what you have is that if you use include with the T at the end, which is include and tag, what you have is that if you modify the code and then save, all the definition of functions will synchronize between what is in the Apple and what is in your code. So you don't have to restart everything from to restart the Apple and so on. The only thing that cannot change is when you change the definition of some structors, because this actually means that the structure change. While the changing function is simple, changing structures is a lot more complex. So my suggestion is to use this package and let's see if I can. Well, otherwise I will share again the screen. Jupyter Island. We have using a device. Now you have, in addition to included T. And which, when you work with included, tracks all the changes. So I think the pipeline would be to continuously, you can continuously modify your code and always use the REPL to work with, to interact with your code. To immediately, you can define a function. The function immediately appears in the REPL, available if you use a device. You can immediately test it if it works, and then you can continue with the confidence that that you have a very short interaction cycle between what you write and testing the actual code. And if you want to use another piece of code that you have on the computer, you can simply use include. And I suggest to look to the module. Which module is a way to get together a collection of function structures and definitions. For example, everything we're seeing for is everything in Flux, for example, in the module Flux, we can say what is imported in this module, what this module exploit, the types, the function, and so on, and what I private, in this case, to the module. If you want to stick to everything more like, say, a normal library. I don't know if this answers your question, if you have any additional question about the workflow. Okay, thanks. So if you have any other question.
I think no one has got questions, we can conclude. And if I can just say a couple of words, I'd like really to thank you, Professor Manzoni, for this opportunity. It's been great. Has been very successful, and we hope that the more initiatives like this will happen in the future. Certainly from our side, we will definitely continue. And yeah, I think you did an amazing job, and we are really grateful for what you did. Thank you very much.
Thank you to you for giving me this opportunity to talk about Julia, and to everyone for listening. And yeah, I was very happy to have this opportunity, and thanks.
Thank you very much, Luca. Bye-bye.
Thank you. Okay. Bye-bye to everyone. Thank you.
Bye.
Bye-bye.
Bye.
Bye-bye.